Good morning. Myself, Sridhar KN, Assistant Professor of Physics, Government First Aid College, Kolar. I am now taking a session on electricity and magnetism, which is the title of the paper of BSc Physics, third semester of Bangalore North University. Corresponding to the 21 session, we will study the magnetic field due to the dipole moment, and we also study the field on the axis of a solenoid of the unit magnetic field and forces. The learning objectives are: students understand the concepts of magnetic dipole moment and learn to derive the expression for the field on the axis of a solenoid. The outcomes: students understood the concept of magnetic dipole moment and are able to derive the expression for the magnetic field due to a straight current carrying conductor. So coming to the magnetic dipole moment. The magnetic dipole moment, represented by the symbol mu, is a vector quantity, and its direction is given by the right hand rule. Will be explained at the end. And this magnetic dipole moment is used to measure the tendency of an object to interact with the external magnetic field. Larger the tendency of the object to interact with the magnetic field, larger will be the magnetic dipole moment, and vice versa. Similar to a compass needle, the magnetic dipole will align itself with the external magnetic field. The magnetic dipole will experience a torque given by tau equals mu cross B naught when it is kept in an external magnetic field. The dipole is kept in an external magnetic field, it will experience a torque in the sense it will experience two equal and opposite forces due to which it rotates, and hence moment of couple, otherwise known as torque, is given by this expression, or mu b sin theta. When this magnetic dipole is aligned parallel to the direction of the external magnetic field B naught, it will be in its lowest energy state. That is, the potential energy will be minimum, and that will be equal to minus mu B naught if it is aligned parallel to the external magnetic field. On the other hand, if it is aligned anti-parallel to B naught, if this is B or B naught external magnetic field, and if this is the direction of the magnetic dipole that is mu, then the potential energy is minimum. Similarly, if this is B or B naught, that is external magnetic field, and if this is mu, which is oppositely directed or anti-parallel, then the potential energy will be maximum, or it is said to be in its highest energy state. In order to find the direction of the magnetic dipole moment, we consider to curl the fingers of the right hand, curl around the loop in the direction of the current. The curled fingers of the right hand gives the direction of current, then the extended right hand thumb gives the direction of magnetic dipole moment, and this is how we measure the direction of magnetic dipole moment. So coming to the field on the axis of a solenoid, let us consider a solenoid of length L. This is the solenoid. Let xy is the axis of the solenoid. Xy represents the axis and R represents the radius of the solenoid. From one end of the solenoid to the axis gives the radius of the solenoid, and there is circles above and below the solenoid represents the number of turns. Total number of turns, which is taken as equal to capital N. And therefore, small n represents the number of turns per unit length. Number of turns per unit length of the solenoid. On the solenoid, we consider a slice AB. AB is a slice. This is AB. A small portion of the solenoid is considered whose thickness is equal to dx. Number of turns in this slice AB will be equal to n into dx, wherein represents the number of turns per unit length and dx gives the thickness, and therefore n into dx gives the number of turns of the solenoid of slice AB. Now, magnetic field at point P at a distance x from the slice is So observe here, point P makes an angle, point P makes an angle theta with B, makes an angle theta 1 with the left end of the solenoid, makes an angle theta 2 with the right end of the solenoid, and A is the distance between point P and small a is the distance between point P and the slice A of the solenoid. Now, by applying the magnetic field at point P is given by the expression dB equals mu naught Ni r square divided by 2 into r square plus x square whole power 3 by 2 into dx. This is the expression for the magnetic field due to a circular coil. As the thickness is dx, so we have considered it as dx itself. This field is along the axis of the solenoid, and the direction depends on the direction of flow of current in the solenoid. From figure, tan theta is equal to opposite by adjacent. Opposite is AB. Opposite is this much, or here to here, which is nothing but equal to radius. Opposite is this value. This is the opposite value, which is nothing but equal to radius, and adjacent is this way. This is the adjacent, which is equal to x. Therefore, tan theta equals r by x, or x will be equal to r by tan theta, or x will become equal to r cot theta. Differentiating this expression, we get dx is equal to minus r cosecant square theta into d theta. Therefore, dB will be therefore equal to, on the previous slide we had dB equals mu naught Ni r square. In the previous slide we had mu naught Ni r square. Whole divided by 2 into r square plus x square whole power 3 by 2. For x and for dx we have substituted this value. That's the only difference that we have made. Therefore, it becomes dB equals minus mu naught Ni r square by 2 r square plus x square whole power 3 by 2 into r cosecant square theta d theta. or rewriting, we get dv equals minus mu naught ni r cube cosecant square theta d theta divided by 2 r cube cosecant cube theta. For the denominator also we have substituted this value. We have substituted it. So substitute ಮಾಡಿದ್ರೆ ಏನಾಗುತ್ತೆ ನೋಡಿ denominator ಅಲ್ಲಿ we get r square plus x square whole power 3 by 2 r square as usual r square itself plus x square is r square cot square theta r square cot square theta r square cot square theta whole power 3 by 2 that is equal to taking r square common r square into 3 by 2 ಆಗುತ್ತೆ square and cube gets cancelled into 1 plus cot square theta 1 plus cot square theta whole power 3 by 2 and this r square whole power 3 by 2 will give rise to r cube as usual and 1 plus cot square theta will become equal to cosecant square theta whole power 3 by 2 and therefore square and half gets cancelled, it becomes cosecant cube theta. 2 as usual we have not changed anything for 2 and therefore finally this cosecant r cubes gets cancelled, cosecant square gets cancelled with cosecant cube and the remaining is therefore dv equals minus mu naught ni by 2 into 1 by cosecant. 1 by cosecant is nothing but equal to sin theta into d theta. Therefore, total magnetic field due to the entire solenoid is, and this dB is only for the small portion of the solenoid which is AB. We want to find the magnetic field due to the entire length of the solenoid. In order to determine the magnetic field at point P due to the entire length of the solenoid, the above expression will be integrated between the limits theta 1 and theta 2. Now therefore B equals mu naught ni by 2 between the limits of integration from this end to this end, that is from theta 1 to theta 2 minus sin theta d theta, and that will be equal to mu naught ni by 2 minus sin theta. Integral of minus sin theta is nothing but cos theta with limits of integration theta 1 and theta 2. Substituting the limits of integration, we get B equals mu naught ni by 2 into cos theta 2 minus cos theta 1. This is the final expression for the magnetic field on the axis of a solenoid. Remember, n is equal to n by L. As small n is number of turns per unit length, therefore small n is equal to capital N by L, where n represents the total number of turns and L represents the length of the solenoid. If point P is at the center of an infinitely long solenoid, if the length of the solenoid is infinity, if the length is equal to infinity, L equals infinity, then theta 1 become almost equal to 180 degree and theta 2 become almost equal to 0 degree. Therefore, the above relation becomes cos 180 minus cos 0. That is this is cos 0 minus cos 180. Cos 0, cos theta 2 minus cos theta 1. Therefore, it is cos 0 minus cos 180 and therefore it will be mu naught ni by 2 the expression is B equals mu naught Ni by 2L or mu naught Ni by 2, mu naught Ni by 2 by 2, that is equal to into cos theta 2 is, that is cos 0, which is 1, minus cos theta 1, that is cos 180, and this is minus 1, therefore minus of minus 1 is plus 1, and therefore this 1 plus 1 gets cancelled with the denominator, and therefore this is mu naught Ni, or simply mu naught Ni by L, mu naught capital N I by L, one and the same, because small n is capital N by L. If point P is at the end of an infinitely long solenoid, if I consider point P at the left end of the solenoid, if this is point P, then theta 1, this is theta 1, this itself is theta 1, therefore theta 1 is 90 degree and theta 2 is almost 0 degree. Therefore B equals mu naught Ni by 2, mu naught Ni by 2 into cos theta 2 is, that is cos 0 is 1, minus cos theta 1 is cos 90, that is 0. Therefore it is equal to mu naught Ni by 2 or mu naught capital Ni by 2L by 2L. If I take small n, then there will be no L. If I take capital N, then there will be an L in the denominator. And this is the expression for the magnetic field at an end of the solenoid. If point P is at the center of the solenoid of length L, if L is the length of the solenoid, then the magnetic field at the center of such a solenoid is, so cos theta 1 will be equal to cos theta 1 will be equal to adjacent by hypotenuse. Cos theta 1, if P is at the center, then this will be equal to L by 2. Then this distance will be equal to L by 2. Adjacent is L by 2. Divided by hypotenuse. So this is the hypotenuse, and this is taken as equal to from Pythagoras theorem, square of this is equal to this square plus this square, right? If I take this as equal to some let me take this as C, yes, and this will be R, this is R. Therefore C square equals R square plus L by 2 whole square, or L square by 4, one and the same, L square by 4. If I take C, then this becomes root. And this is given here. Similarly, cos theta 2 equals adjacent by hypotenuse on the other side, it will be the same. But for cos theta 1, it is taken as negative as it is to the left. Therefore, B equals mu naught Ni by 2 into cos theta 2 minus cos theta 1. The minus of minus has become plus. As the denominators being the same, the numerators can be added up. So it is added over here. Mu naught Ni by 2 into 2 into L plus 2, that is L plus 2 plus L plus 2 will be 2 into L plus 2 divided by R square plus L square by 4 whole power half. Or this is mu naught mu naught ni L divided by 2 into taking LCM, it will be 4R square plus L square whole divided by 4 whole power half. And this 2 gets cancelled with this 4. If I take 4 out of the root, it becomes 2, therefore 2 and 2 gets cancelled. And this is therefore mu naught ni L, and here there should be L, or it becomes mu naught capital Ni whole divided by 4R square plus L square whole power half. This is the expression for the magnetic field at the center of a solenoid of length L. So coming to the multiple choice questions. What is the magnetic field outside a solenoid? The magnetic field outside a solenoid is 0. There will be no magnetic field outside the solenoid due to the current flowing through it. And the second one, the magnetic field at the center of a solenoid is B. If the length of the solenoid is halved and the same wire is wound into layers, the new magnetic field will be B equals, we have mu naught Ni by L mu naught Ni by L and that is equal to, or similarly B dash equals mu naught into B dash equals number of turns in half the length remain the same into I divided by length has been reduced to half, therefore it is L by 2, or this is equal to 2 into mu naught Ni by L or B dash equals 2B. This is the new magnetic field, and this is the correct answer. Coming to the third MCQ, a solenoid of length 20 cm, radius 2 cm, is closely wound with 200 turns. The magnetic intensity at either end of the solenoid when the current in the winding is 5 ampere is. We have the expression for magnetic intensity. It is given by H equals B by mu naught. B by mu naught is called the magnetic intensity H, and that is equal to, at an end of the solenoid, it will be Ni by 2L. Ni by 2L. And this will be equal to N is 200 into I is 5 ampere divided by 2 into L is 0.2 or 20 into 10 power minus 2. I will take 0.2 itself. 0.2. So this becomes 200 by 0.2 is nothing but equal to 1000. 1000 into, this gives 2.5, 5 by 2 into 2.5. Therefore, it will be equal to 2500. This is the answer. 2500 ampere per meter is the magnetic field intensity at an end of the solenoid. Now, the next question. A solenoid of length 0.5 meter has a radius of 1 centimeter and is made up of 500 turns. It carries a current of 5 ampere. The magnetic field inside the solenoid is B equals, magnetic field inside the solenoid is B equals mu naught Ni by L. Mu naught Ni by L. That is equal to, mu naught is 4 pi into 10 power minus 7. The value of mu naught is 4 pi into 10 power minus 7 into N is 500 into I is 5 ampere again, whole divided by L is mu naught Ni by L. L is 0.5 meter. 0.5 meter. That will be equal to, and this gives 1000 as usual, 1000. This is 1000. And 4 into 5 is 20. 20 into 3.14, that is pi. 3.14 into 10 power minus 4. Minus 7 plus 3 here, therefore it is minus 4, or it is 2 into 3.14. 2 into 3.14 is 6.28. 6.28 into 10 power minus 3. I have taken it as 2 instead of 20, and therefore 0 will reduce here, 10 power minus 3. This is the magnetic field at the center of the solenoid, 6.28 into 10 power minus 3 Tesla. And the last one, a long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns is halved, the new magnetic field is. Therefore, we have B equals mu naught Ni by 2, just mu naught Ni. B equals mu naught Ni. B equals mu naught Ni. And B dash is mu naught N is N by 2. Number of turns has been reduced into number of turns has been reduced, whereas the current is doubled to I. Therefore, it will be equal to mu naught Ni, and that will be equal to B. This is the answer.